Okay, everybody, welcome back. Today, we're going to talk about nozzles and diffusers in a lot more detail. But before we get started on that, let's go ahead and go over what we covered last time. So, in the last lecture, we came up with a lot of very important relationships in terms of the Mach number. So things like the stagnation enthalpy, the stagnation temperature, and the stagnation pressure, all in terms of the Mach number. We came up with the so-called working equations, things like ratios of the properties between two different points in a system, where these were just functions of the Mach numbers at those two locations, the ratio of specific heats, and any sort of irreversible losses, delta SI. And then we ended the lecture by talking about this concept of the sonic reference state. Sonic/star reference, which is basically go to m equals 1 isentropically, and then you reach the sonic reference state. And then we had this relation that we derived from the working equation for area, where A2 star over A1 star is equal to E to the delta S over R, which implied this relationship PT1 A1 star is equal to PT2 A2 star. And that's where we ended the lecture. Okay, another thing that we talked about in the lecture was nozzles and diffusers, and that's going to be the main topic of the lecture today. But before we go there, I want to talk about a different type of relation, which is derived from the working equations, called isentropic relations. Okay? Now, these relations are so called because they're about relationships between a state and in a given reference state, and the process that you go from a given state to a reference state, whether it be the stagnation state or the sonic reference state, is an isentropic process. So then we call these isentropic relations. So, recall from the last lecture, the working equation for area was A2 over A1 is equal to M1 over M2 times the quantity 1 plus gamma minus 1 over 2 times M2 squared rather, divided by the quantity 1 plus gamma minus 1 over 2, let's make that a little bit cleaner there, gamma minus 1 over 2 M1 squared. That entire quantity raised to the power gamma plus 1 over 2 times quantity gamma minus 1. All that multiplied by E to the delta S over R. Okay, so if we use this relation between its general state and its sonic reference, so let's say let A1 just be called A, so your cross-sectional area for a random state. And then let's say that A2, the state that it's transitioning to, or the second state that you're trying to define for this ratio, is equal to A star. All right. Well, in that case, in fact, let's actually flip these because I don't want to accidentally make a typo here. We're going to let A2 be A and A1 be A star, so that we obtain this relationship, which is A over A star, and then we set it equal to what? Well, we'll drop the subscript on all the M2s, and then like I said, for the star reference state, m is equal to 1, right? So all the m1s just go to 1, and you obtain this relationship where you have 1 over m times the quantity 1 plus gamma minus 1 over 2 m squared divided by gamma plus 1 quantity divided by 2. Okay, and then we also have this exponent to gamma minus 1. Okay, and then what about the exponent part? Well, like we said, this is about an isentropic process, so delta S is equal to 0, and that component goes away. Okay, and an important thing to notice is that this is just a function of gamma and m, the Mach number at the given state. Okay, so the big thing is that this formula here can be pre-calculated and tabulated. And in fact, in your textbook, this is tabulated in the appendices. I can't remember which appendix exactly. I think it's Appendix G in Zucker and Biblar's. But you'll see that this relationship here that I'm drawing a box around will become quite important, especially in the analysis of propulsion systems. I mean, this is looking kind of 7 or 8 weeks, or maybe 6 weeks in the future in this class, but that relationship, that area-Mach relation, will become very important when we're, equating mass flow rates across different points in the propulsion system. So great. Now, to give you an idea of how you actually use these values, suppose we have gamma, we have the ratio of two areas, A1 and A2, and we know the Mach number at station 1. And we want M2, right? Okay, so we know the ratio of the areas, and we want M2. Now we could just plug it into this formula here where we have A2 over A1 and solve for M2, but that's complicated because it's in a sense it's like a transcendental equation, right? Like you have M2 raised to a really complicated exponential, and it becomes difficult to solve for it algebraically. So what you can do is you say that you set A2 over A2 star equal to A2 over A1 times A1 over A1 star times A1 star over A2 star, right? And then also we're going to assume 1 to 2 isentropic. Got to write that down there. So we're assuming the state, the transition from state 1 to 2 is isentropic. And then, okay, what are we looking at here? Well, because the state 1 to 2 is isentropic, this A1 over A1 star over A2 star is just equal to 1, right? That's because of that isentropic thing. Now, this thing is known, A2 over A1, because we know the geometry of our system. And then what are the rest of these two? Well, we know what M1 is, right? So if we know what M1, then we know this, we can calculate this using M1, right? Via the formula above. And then by those three things, we can get some value let's just call it star, right? And then we can use a table to determine N2 that yields, f of N2 is equal to star, right? So you'll have a table with a bunch of entries from a Mach number on the left, and then one of the columns will be this area Mach relation A over A star. And then you'll go here and you'll search for the value that you just calculated in that column and look over and pick the Mach number that corresponds to that value. And then that would be M2 in this case. And that sort of process you're going to do over and over when you're doing the problems in this class. Practice, that'd be done via software. You'd have something that would, have all of these relations codified. But, eventually you're going to be taking paper exams in this course, so we kind of have to rely on the property tables for you to do these types of problems, at least for now, until I can think of a better way to do this. Okay, so you could do that. Now, one note is that you actually will get two solutions. You will obtain two solutions. But one will be subsonic and one will be supersonic, and then you have to use your physical intuition to eliminate, which one is the spurious. So 1 m greater than 1, 1 m less than 1. You must use intuition to eliminate the spurious solution. And as you think about this, you might guess the way you're going to do that in general is you're going to ask yourself, as I go from state 1 to state 2 based on the things that I know, should my Mach number be going up or down? That's really the question, right? So if you have a subsonic, or let's say you start with a subsonic Mach number and you're in a converging duct, you know that there's no way for you to reach a supersonic Mach number. In fact, if you start subsonic, whether you're a converging or a diverging duct, you would not expect to go supersonic, right? Because you would need to have some sort of converging, diverging duct to achieve that. So you look at your overall system, the things that you know, and the things that are happening between state 1 and state 2, and that allows you to determine which of the solutions, the subsonic or supersonic solution, is the one that's reasonable and possible. Okay. So let's look at another sort of example here that'll hopefully be a bit more concrete. So we're going to look at a diverging duct. So this is state 2, this is state 1. Okay, and we have the following given information, which is that A2 over A1 is equal to 5 over 2. We have that the total heat transfer and shaft work in the system is 0. We have that the ratio of specific heats, gamma, is equal to 1.4. In other words, we're working with air here. And then we have that the change in entropy from 1 to 2, the total change is 0. So we have no losses, saying that it's isentropic from 1 to 2. We also know that at the Mach number at the entrance is 0. Okay, it's quiescent, let's say. And then we have that P1 is equal to 4 bar. Okay, so what we want to find here is M2 and P2. Okay. So I actually I had a moment there where I was a little confused because I was thinking Mach number 1 equals 0. That doesn't make sense. So there's an error in my notes here actually. So the Mach number here is meant to be 0.5, not 0. Okay, and now things will actually make a bit more sense. Okay, so let's proceed from here. Okay, so the way that we do this, because we have the Mach number at 0.1 and we have the area ratio, we should be able to find M2 just with those two pieces of information alone. So like we did above, we kind of do this reasoning, or we expand out and do this canceling fraction deal here, where we pull out information that we know. So we know what A2 over A1 is, right? That value is given, and then we multiply that by A1 over A1 star. That can be calculated from M1. And then we have A1 star over A2, and we know from our physical understanding, because delta S1, 2 is 0, that goes to 1. So that those three things multiplied by each other are 5 over 2 times, this is from the table, 1.3398, right? This was a lookup value for M1 equals 0.5. And then the last value is just 1 because it's isentropic. And then what you end up with for those values is 3.35. And if you go into the tables and look that up, that tells you that M2 is equal to 0.175 or 2.75. Right, and so which one of those is the correct answer? Well, of course, like I was just saying before, if you're starting subsonic, you're not going to suddenly reach a supersonic Mach number in either a strictly converging or strictly diverging nozzle, right? So we know that the 2.75 solution is the spurious one, and that M2 is equal to 1.75. Okay? So now we can use that value to find what P2 is, because now that we know what M2 is, we can use that to look up the table value for P2 over PT2. Okay? Because that's another isentropic relation. So we showed that, for example, that P over PT is just a function of the Mach number, so that's also tabulated. So we can write down P2, and we can expand it as a bunch of these fractions between canceling fractions, let's say. So we know that PT2 over PT1, that value is just going to be 1, because the state transition from 1 to 2 is isentropic. And that PT1 over P1 times P1. So you can see everything cancels here to give you PT2. We know that this guy is a function of M2, which we can look up at the table. Likewise with this guy, this is a function of M1, which we can look up in the table, and then this is equal to 1 because because the transition from 1 to 2 is isentropic, right? So what this ends up giving us is 0.9788 times 1.186. Okay, those are those two values that we looked at in the table, times the previous pressure at state 1, and that is equal to 4.64 bar. Okay? So that is perfectly fine. That's how you can use these sort of isentropic relations in practice, as opposed to having to do some sort of root finding algorithm to solve these equations. All right, so you'll be doing that over and over and over in the homework. So kind of get familiar with this idea of hunting. If you're given a Mach number, that gives you all the isentropic relations. So that gives you all the ratios between static values and stagnation and sonic values at a specific points. And then you can also hunt down a Mach number by knowing the the ratios between static values and reference state values at those points. Okay, so let's look at now let's move on and let's have a discussion about nozzle operation. So remember in the last lecture we had a discussion about choked flow, and in fact I may not have actually written that down, but choked flow as a definition is when you have Mach 1 flow at the plane of minimum area. Okay, so yeah, I don't think I actually wrote that down. So let's just go ahead and write that down. So choked flow is when you have, just put simply, okay, m equals 1 at plane of minimum area in a nozzle. Okay, just so you have that written down somewhere. So let's recall our discussion about that, right? So what we're going to do is we're going to derive the pressure ratio that gives rise to choke flow. So let's draw sort of a converging duct here, okay? And then we'll have state 2 over here where we have P2 and then an area which that occurs A2. And then we have upstream T1, P1, static pressure and temperature. And then we're going to say that the upstream is quiescent, meaning it's just a big tank full of some kind of gas that's not moving. Okay? And then P2 is what is called the receiver or back pressure. You'll see it called both of those things fairly often. Okay? So we have this large stagnant supply tank. And what that means is the flow is stagnant, right? So because of that, the static properties of the same thing are the same value as the stagnation properties. Remember, we have that Tt is equal to T times this quantity, 1 plus gamma minus 1 over 2 m squared, right? Well, if m is equal to 0, that in other words, the flow is not moving, then Tt is just equal to Pt, T, and then likewise for the stagnation pressure. So we know that Pt is equal to P, and Tt is equal to T. And this is at state 1 in particular, Tt1 and Pt1. Okay? So these things are the same. We're also going to assume no heat or work being done. So that means that the stagnation enthalpy is the same between state 2 and 1. Okay, so that's another thing. So remember, I said that this back when I mentioned it, but the stagnation enthalpy is conserved whenever there's no heat occurring between two different spots. Okay, because this is we're going to assume perfect gas as well. That means that the enthalpy in general is just equal to Cp times T. So if the two stagnation enthalpies are the same between those 2 points, and the stagnation and the specific heat values are constant, which is another thing that perfect gas signifies, then this implies that the stagnation temperatures between state 1 and 2 are equivalent as well. Okay. And then we know that there's this sort of delta P, which is equal to P2 minus P1 is what's driving the flow. Okay, so now let's assume that we lowered P2 such that M2 is equal to 1. Right, so we lowered it just to that perfect point. Then P2 is equal to PT2 times this quantity 1 plus gamma minus 1 over 2. Now you normally have m squared here, but we're going to have 1 squared because we're assuming that m2 is equal to 1. And this is gamma over gamma minus 1. Yeah, this should be a negative up here. Correct, yeah, because we divided it across. Okay, so what that results in is that P2 over PT2 is equal to 0.5283. Okay, and this ratio defines the so-called critical pressure that gives rise to choke flow. Okay, go ahead and box this. So in general, this is actually how you're going to check if the flow is choked in a nozzle. You're going to compare the back pressure or the receiver pressure to the upstream stagnation pressure. Okay, because you can think of the upstream stagnation pressure as kind of the total available pressure there is to push the flow. And once you drop it to this level, the flow is choked. If you drop it lower than that, the flow remains choked, right? Why? Because as soon as the flow is choked, the upstream flow, remember, is completely blind to anything beyond the throat. So dropping the back pressure any further than that is not going to affect the dynamics from the throat going upstream. And so it just remains choked. So your condition for choking is something like the back pressure needs to be lower, or the ratio of the back pressure to the upstream stagnation pressure needs to be lower than this value, this 0.528. Okay, so one thing to note is that in an isentropic nozzle, just a nozzle that is lossless, we know that PT2 is equal to PT1. So in general, you can use this value to check if P2 over PT1, which was the known value, is less than or equal to 0.5283, which would imply choked flow. Actually, to use this inequality, what you're going to be talking about is actually the receiver pressure or the back pressure in general, because the the static pressure at the throat is actually going to have, because at the throat m is equal to 1, so you're actually always going to have this sort of equivalence here. So P2 is kind of, in a sense, fixed, P2 right at the throat, but the back pressure that gives rise to that, as long as the ratio of the back pressure to the upstream stagnation pressure is less than or equal to this value, then you'll get choke flow. Okay, so don't get too confused. The idea that you could have a certain static pressure right at the throat and then a different or lower pressure downstream of the throat will make more sense as we actually elucidate what happens when you what kind of shock wave structures exist beyond the throat in these nozzle structures when you push the back pressure lower. But just rest assured that your general check in the future, and I say this because you'll be doing this check a lot in this class, is you look at what the back pressure is, that is the receiver pressure, and you're comparing that to the upstream stagnation pressure, that is the stagnation pressure upstream of the throat. Okay. Now things can get more complicated if you have a supersonic Mach number coming into the nozzle and that sort of stuff, but we'll leave that discussion for later when things get a little bit more complicated. Okay, so what we're going to do here is it's almost an aside, but it is us sort of proceeding down this route. So one thing that you can show for isentropic flow this relationship m dot over A, so this is the area normalized mass flow rate, is equal to the Mach number times 1 plus gamma minus 1 over 2 m squared, oops, not m2, m squared, that whole thing raised to the minus gamma plus 1 over 2 gamma minus 1, multiplied by gamma over r raised to the 1/2 power times pt over the stagnation temperature. Okay, so what this tells us is that the flow rate is maximized when A is equal to A star, which corresponds to m equals 1, of course. Okay? M dot over A max is equal to m dot over A star, which is equal to gamma over r times the quantity 1 over gamma plus 1 raised to the power gamma plus 1 over gamma minus 1, that whole thing raised to the 1/2 power times pt over square root of tt, which, to boil it down, is some constant times pt over the square root of tt, right? So for fixed stagnation temperature, stagnation pressure, and sonic area, the maximum mass flow rate that we can reach is constant. If only the stagnation pressure goes up, that tells us that our maximum mass flow rate goes up. If only the stagnation temperature goes up, that tells us the maximum mass flow rate goes down. And then if only the sonic area goes up, that corresponds to the maximum mass flow rate going up. And these are actually pretty intuitive. So like, for example, if the sonic area is going up, that means that the cross-sectional area of the throat that the flow is going through at this choke condition is just bigger. So of course the mass flow rate is going to be larger, right? And if the pressure is going up, that's sort of analogous to you know, driving a bigger density, more flow being pushed through, whereas temperature going up makes the gas more diffuse, and therefore like lower density, and that's why the mass flow rate might go down. Okay, so they're kind of intuitive to work through. Okay, hopefully it was clear why we have. In fact, it probably wasn't clear at all why this quantity is maximized at m=1. But you can go ahead and do that using you know, calculus if you like. But just take my word for it that is where the flow rate is maximized for that relationship. Okay. There might be a more detailed treatment of that in the textbook. Okay. So that was just a little kind of aside to discuss the mass flow rate there. Give you an idea of how your upstream stagnation conditions affect what kind of flow rates you can achieve. What we're going to talk about now is we're going to go back to the type of nozzle that we alluded to in the previous lecture, where we accelerate flow to the Mach number at the throat, but then continue to accelerate it by adding a diverging section. Or in other words, we're going to talk about the converging-diverging nozzle. Which is also known as the de Laval nozzle. Okay. So let's imagine we have this scenario, sort of like a big tank attached to that converges down. Sorry, I can't get this two halves to kind of match each other there. And then a bell-shaped diverging section here. I don't know why the bottom lines are so much more difficult for me to draw. That's better. Okay, and then we say that this is state 2, state 3 is at the exit, and then state 1 over here, which is sort of, we'll just kind of define it loosely as just the upstream condition with P1, T1. And then your, what's called your design operation is where you have, at state 1 is some sort of subsonic flow. At state 2, you're exactly sonic, or the flow is choked. And then at state 3, you have supersonic flow. So when you have these three conditions all happening at the same time, we call this design we call this the design operation. Okay, so to throw in some actual numbers here, let's say that P1 is equal to 100 psi absolute. We'll have T1 be equal to 600 degrees Rankine. And then we'll have A3 over A2 be equal to 2.494. Okay, and then the question becomes, find P3 to ensure design operation. So we want supersonic flow at the exit, right? So the first thing that we want to do is we want to find what the Mach number at state 3 would be. And the way we can do that is by finding A3 over A3 star, using the fact that we know what the Mach number at state 2 is, and we know what the area ratio between 3 and 2 is. Okay, so this is equal to A3 over A2, A2 over A2 star. We know what that is. And then we also have A2 star over A3 star. Now we're going to assume that the flow is isentropic from state 2 to 3, because why would we make our design operation such that we have some sort of losses occurring between our two states? So that's isentropic. So this goes, whoops, this goes to 1. And then, because it's isentropic. And then this is equal to 1 because M2 is equal to 1, right? So A2 is equal to A2 star, with the same thing. And so basically this ratio is just the given area ratio. It's 2.494. And if we look at the supersonic section of the isentropic table, this tells us that M3 is equal to 2.44. Now, you will find a subsonic M3, but we're looking for the supersonic operation, so we're looking for the supersonic root. And then if we can read off the pressure, the stagnation pressure ratios and the stagnation temperature ratios from the table, from the same row of that table. So P3 over PT3 is 0.0643, and T3 over TT3 is 0.4565. Okay. So now we can pretty much calculate P3 right away, because the operation starting from P1 all the way to T3 is completely isentropic. And we're assuming that the flow, in fact, I didn't write this down, but we're assuming that the flow upstream is quiescent. So that means that, this thing is going to imply that PT1 is equal to P1. Okay. So because of that, we have P3. We can write this as P3 over PT3, PT3 over PT1, and then PT1. And we're making the assumption that it's isentropic from state 1 to state 3. So that means that the stagnation pressure does not change. So this goes to 1. We just wrote down what that value was, and we know what T1 is because it's the same as P1, because the flow is stagnant upstream. And that allows us to write that P3 is equal to 6.43 psi. So that's what you have to lower the back pressure, the receiver pressure to reach your design operation. And this is referred to as the third critical. Okay, so design operation and third critical, these things mean the same thing. Okay? They're interchangeable. So now we're going to draw a pressure diagram that you'll see several times in the course. And it's a pressure, it shows the evolution of the pressure as a function of position in a converging diverging nozzle, where this location is the throat and this location is the exit. Okay, and the scenario that we just worked through, the third critical, would be this line where it goes smoothly through the throat, and then it changes concavity at the throat and goes to the exit, like right here. And then this pressure here is the third critical sort of back pressure operating condition. Now, there's also, so remember, when we looked for this value of A3 over A3 star in the tables to pull out M3, we looked at the supersonic value of M3 right away because that was the operating condition we were looking for. But the other root of that equation for the same area ratio is what's called the first critical or the subsonic branch of this pressure diagram, and it looks like this. It's just a kind of a mirror image going up this way, and this is the first critical. Okay, and in this diagram, you can sort of characterize everything above the first critical operating condition as what's called the Venturi regime. And that's sort of, the qualitative way of describing a Venturi tube or Venturi operation is where you have flow that starts subsonic, speeds up, and then slows down as it goes into the diverging duct, sort of the type of stuff that might be more intuitive to you. And then this regime is what's called a non-isentropic regime. And that regime is interesting. We're going to talk about it in detail. Basically what's happening in that regime is that shocks are occurring in the nozzle. Let me change the direction of these so it's more distinct from the Venturi. So we'll do like this. So in there, we have shocks in the nozzle. And we'll talk about that more later. More on this later. Okay, the second critical that has seemingly been left out here will have to do with those shocks in the nozzle. Okay, we'll talk about that in plenty of detail, so don't worry about that. Okay, and then down here, if you chose a back pressure that's sort of below the third critical, then you'd have expansion waves outside the nozzle. And again, that's something that we will cover more later. But inside the nozzle, it'd be the same as though you're at the third critical, if your back pressure is lower than the third critical. Okay, so that's and we should think of this as like a preview. We're going to cover all this stuff in much greater detail, but this third critical operation is really what you aim for when you design a nozzle. This last section that we're going to cover today in this perhaps slightly shorter lecture is nozzle performance. So Zucker and Villars tried to come up with a way to define some efficiencies for nozzles and diffusers. So to account for losses, we would define the nozzle efficiency eta n as the change in kinetic energy realized by the nozzle divided by the change in kinetic energy of the ideal case with no losses. So, most nozzles have negligible heat transfer Q and no shaft work. So the energy equation just tells us that HT1 plus Q equals WS plus HT2. Both of these just go to 0. So we know that the stagnation enthalpy remains constant in the nozzle, which tells us that H1 minus H2 is equal to V2 squared minus V1 squared over 2. So this allows us to write the nozzle efficiency as essentially the change in enthalpy between the two states, right? So because this is essentially the change in enthalpy between the two states is the change in kinetic energy, okay? Because there's no heat and work being done. So you can also express it as sort of the actual change in enthalpy that you realize divided by the ideal change in enthalpy, which you can express as H2 minus H1 divided by H2S minus H1. And that means that you reached your back pressure. In other words, the pressure evolves to match whatever the pressure is at the receiver via an isentropic process. So that's when you would end up with H2S. Okay, so let's go ahead and draw this in a diagram to give you an idea of what I'm saying here. So let's say we have an HS diagram. HS. And you know, something I should say is that an HS diagram, so in our context, we're almost always talking about something like a perfect gas. So an HS diagram is basically a TS diagram. Well, why do we draw TS diagrams? Why do we draw PV diagrams? Well, a TS diagram, the reason why we draw that is because if you let's say you drew a cycle on a HS diagram. This is just let's just say that I'm going to erase this, but let's say the cycle looks like this. How do you obtain this area enclosed there, right? What you would be doing is you would take the integral of the legs of each, the cycle, say, of T ds. Right? What's that? What's TDS? It's the heat. There's going to be, if we're talking about ideal cycles, so in an ideal cycle, this is just going to be like your net heat transfer. Okay, so that's why you draw the diagram that way, is because you can kind of interpret the area enclosed by a process or by a cycle as the heat transfer. Same with a PV diagram. If you have a P and a V, then if you look at the cycle, the way that you get that area there, that's the integral of PdV. Well, what's that? That's the work. Okay, so you can interpret the area enclosed by cycles on a PV diagram as the work. Of course, not everything is a perfect gas. Not every process is ideal, so you can't always interpret it that way. But I don't think I had actually motivated drawing an HS diagram versus any other, and often classes don't really, professors don't really do that. So there you go. That's why we draw HS diagrams. There's probably other reasons, but at least that's the main reason I can think of. Okay, so then let's say that we have state 1 here, and then the true state 2 is over here. And let's draw some iso bars. So that means lines of constant pressure on this diagram. They look like this. Okay. So this is like P2, this is P1. And the actual sort of process looks like this. It goes in that direction from state 1 to 2. And if we were to draw 2S on this diagram, we would want to go straight down along an isentrope, or a line of constant entropy, and this is state 2S. Okay, and you can see that the enthalpy value for the state 2S is larger. This is H2S, H2S, and this is H2. Right, so you can generally see here that, if entropy is produced, then you get less change in enthalpy as you go from P1, which is your starting pressure, to P2, which is your receiver pressure at the end of the system. Okay. Did I change the zoom here? Yeah, I did a little bit. Okay, so you can see there why that's a sensible definition of performance. Now, diffuser performance. Yeah. This is actually, you know, borrow in the actual propulsion field. Diffusers are evaluated by the total pressure recovery factor, called eta R. This is the total pressure recovery factor. And it's equal to the stagnation pressure at the exit over PT1. And then we showed through the stagnation pressure energy equation that this is just e to the minus delta S over R, right? So it's sort of a direct way of measuring the losses. Okay, it's like a literal a direct measure of the losses. You know, I should say, you know, stag, fresh, energy equation when, you know, Q and WS are equal to 0, right? So these that's when you get this equivalence here. But what something that Zecker and Miglars do is they actually try to define a diffuser efficiency, an actual diffuser efficiency. So we can define a diffuser efficiency in analogy to the above as eta D equal to the pressure drop, the realized pressure drop divided by the ideal pressure drop. Okay, and this is because diffusers turn kinetic energy into higher pressure generally. Okay, and then we can kind of draw this on an HS diagram as well. HS. Let's say that we have a stagnation state 1T, another stagnation state 2T. This will be 2S. Okay, and then this will be down here. This will be stagnation. This will be state 1. So if you go straight up on the isentrope, you hit 2S, and then if you keep going up, this is your 1T, okay? And then our second state, we have to drop it down here. We'll say that it's like this, okay? It has the same enthalpy value as 2S, state 2, and then our state transition is that little line there, okay? And then we'll draw a bunch of iso bars. They on this diagram, this should be like a little bit sort of shallower than this, but I'll do my best drawing these. Okay, so this is PT1, this is PT2, this is P2S, this is P2, and this is P1. Okay, so generally you can see that, you know, we're getting the same change in kinetic energy between state 1 and 2 and state 2 and 2S, but we're getting a bigger change in pressure between 1 and 2S as opposed to 1 and 2. Okay, so we're getting a bigger payoff. So we're spending the same amount of kinetic energy, but getting less pressure change payoff. Okay. Okay, so like I said, this isn't actually something that's really used in the field, but I do think it's useful talking about it because it's nice to help you think about what the nozzles and diffusers are doing. In the diffuser case, how we're, the definition was changing enthalpy into kinetic energy and vice versa, but you can talk about it in terms of pressure on the diffuser side. So that should give you a nice sort of measure of these two of nozzles and diffusers, and then also a little bit of, as far as the rest of the lecture, a little bit of an introduction into how we work our way through nozzles and diffusers mathematically by using these isentropic relations, and then a little bit of an intro into the math surrounding the converging-diverging nozzle, and we'll go into that in much more detail. Part of which will require us to learn about standing normal shocks, which is the topic of the next lecture. So I look forward to seeing you in that one. Thanks for listening, and I'll see you next time.